Now, another method they use. Imagine we've got a little terrain, it's a bit hard to see how it is. And here's our sun, it's out on one of the limbs. And it's actually orbiting. It takes goes once around our galaxy, about 250 million years. And all the stars are orbiting, they're all moving. They all have their own orbits, some may take more than a quarter billion years, some may take less. But they're all orbiting around and around and around. Now if you imagine we're looking at this field of masses of stars, the ones further away won't appear to move, but some of the ones closer in, if we had, if you imagine a gigantic time lapse, if we had a gigantic time lapse taking a picture every 100 years, we might see something like this. Oh, it moved. Where was supposed to go past? There they go. Right, so we would see some of these stars just fly past, perhaps in a matter of several thousand years. Some of them would just randomly go past. But of course, as they're moving past, some of them may line up exactly, just for a short time, with others. So our sun moves about 200 kilometres every second through the galaxy. Some of the stars move faster, some move slower, but they're all moving somewhere around 200 kilometres every second. And if some of these were to line up exactly, imagine we've got a star here that's a long, long way away, so it doesn't appear to move. And we can see all this light coming towards us. And here's another one of our stars. It's got a little planet orbiting it. And it's just randomly drifting up this way. With time, it gets a little bit closer. And the gravity from the star pulls the light off course. It deflects it slightly. And so some of the light won't get to us. And so it will appear to get a little bit dimmer as this star starts to get close to the alignment of the star behind it. And with time, it'll move further and it'll bend the light more differently. So the brightness of that background star will appear to change with time. As the star slowly drifts even further, it'll change the brightness again. If it has a planet orbiting it, it won't be a simple change, so it won't be just like this dot moving in front. It'll be a little bit more complex because it's got the planet as well contributing to this change of brightness. And so by doing a lot of calculation, they can determine that there are planets orbiting these stars as they just happen to line up. And of course, after a period of time, that star will have drifted away and its gravity no longer affects the light from this distant star. It's gone, that's it. It may take a period of weeks to perhaps several months for that star to gradually drift past the front of the other one. So you imagine if you've got a star that's 1,000,000 kilometres across and the one in front is moving at 200 kilometres per second, it takes a while to traverse that 1,000,000 kilometre star. Even though it looks like a point, it's still 1,000,000 kilometres across. So it could take weeks, but once it's over, that's the end of it. You don't get to replay it, it doesn't happen again. You just have to look at the stars and when this is starting, start measuring it very, very carefully. You get no prediction that it's about to happen, it just happens, and when it's happened, it's gone. If you didn't get it, you won't get it. So you imagine these are very, very rare that you just happen to have two stars drifting past one another. Very rare. They've only found about 11 planets using this method. I just realised I missed something. We'll just harken back to our Kepler telescope. I forgot I had this demonstration on. I just remembered it when I was doing this. So you imagine we've got Kepler, right, looking at all these stars. So here's the star field that Kepler's looking at. And it's looking for planets going in front of these stars. And as they go past, the stars will get a little bit dimmer. So if we were to magnify that change in brightness, this is the sort of effect that it's looking at, only much more magnified. So we see some of these stars blink sort of dimmer and then bright again, periodically, as the planets go in front. Some of them don't have stars, they have planets, and so they don't flicker or anything. So that's basically what the Kepler telescope is looking at, only much less significant than what you see in my little model. Good thing I remembered that. So why don't we just take pictures? Why don't we just take pictures of stars with planets going around them? Well, the problem is that the stars are very, very bright compared to their planets. If we were to actually go to Alpha Centauri and look back at the sun would appear to be about the same brightness as what Alpha Centauri is to us, because they're comparable stars. So you've got this star which would appear to be about magnitude -1, so it's quite as bright as Alpha Centauri. The Earth would be very, very close, but at magnitude 23. If anyone knows anything about magnitudes, they know magnitude 23 is very, very dim. That is how bright Jupiter's smallest moon is, which is a piece of rock something like 4 or 5 kilometres across. That's about how bright the Earth would be from Alpha Centauri, sitting right next to, less than a second mark, like a hair's breadth away from this very bright star. So it's very, very difficult to take a picture because it's got a brightness difference of 1.5 billion to 1. So our sun would be 1.5 billion times brighter than what the Earth would appear. It's very difficult to take photos directly. But they have, the first one they did was Sponholm, which is more or less directly above around this time of year, September, October. Very bright star, pretty much directly overhead at that particular time of year. The only significantly bright one in that area at that time of year. And they took this picture, and they noticed that it has this, the star is actually here, they've put like what they call an occulting bar thing across the top of the star to block out most of the light. And it's got this huge mass of dust around it, huge. And they noticed that right down in here, you can't see very well, in here there's a dot, and the dot just moved very progressively. From 2004 to 2000, I think that's 8. Yeah, to 2008. It moved, and they could calculate the orbit. And this, all the other stuff just didn't move randomly. This little dot, I think that dot's trying to move or something, continued. And they were able to calculate that it's about Jupiter size. It's about 800, nearly 900 years to go around once. Much, much further than Pluto. Pluto only takes 250 years, so nearly 4 times the length that Pluto takes to get around, about 3 times the distance. Another one they took an image of. This was taken in infrared, so basically they're taking an image of the heat. They've blocked out the star, and there's these little hot spots in an area around the star. There's another one because there's 4 planets, but it's not on this image. And these other bright bits, there appears to be a lot of dust around there, and these are just warm pieces of dust, if you like. They could be many tens of thousands or hundreds of thousands of kilometres across, but they're just hot spots. And these particular ones appear to be planets that are orbiting the star. And they vary in size from about 5 to 7 times the mass of Jupiter. So what about some actual exoplanets that we know something more about? There's one, you'll find they have some pretty boring names like HAT P1b. It's orbiting a binary system. So there's actually 2 stars, but it's orbiting one of the stars. The other star is a long way away, and it's orbiting the other star, and the planet is actually orbiting just one of those stars on its own. And they've worked out that it's actually bigger than Jupiter, but it only weighs half as much. It's actually the least dense planet they've found so far. So they've termed it a powder puff planet because it's basically, they would imagine it would just be gas that's all puffed up. So it's a huge ball of nothing, if you like. Another one, Kepler 16b, so this was discovered by the Kepler telescope. It's also orbiting a binary star, but it's orbiting the 2 stars. So you've got 2 stars here, and the planet is orbiting both of the stars while the 2 stars orbit one another closer in. It's about 1/3 the size of Jupiter. So if you look at this simulation, you can see the two stars going around one another. That's a period of 41 days, and then this little blue planet goes around every 228. So it takes about 9 months to go around these two stars that are spinning around every 40 odd days. So they take about 7 weeks to do one orbit. Now if anyone saw the movie Star Wars, they had a planet there called Tatooine which had 2 suns. So perhaps a good name for that planet would be Tatooine. It hasn't been named yet, but perhaps if you're on that planet you might see something like that with the sun set with 2 stars. We found another one which has got an even less easy to remember name, J1719-1438. That orbits a pulsar. So a pulsar is basically a star that's exploded as a supernova. And this planet is orbiting very, very close. And they've been able to determine that it seems to be made almost completely of carbon. What it actually is a remnant of a star, or what they call a white dwarf. And the gravity from the pulsar has stripped most of the atmosphere away from the remainder of the white dwarf, and it's just left this carbon core, which was created by that star as it basically got to the end of its life. It was creating carbon, and then not long after that, that was sort of the end of the fusion. It sort of went a little bit further, and all that stuff's been stripped away. But because they know it seems to be made of carbon, but it's so close to this pulsar that the gravity should just pull this carbon apart, but it hasn't. So they theorised that there's only one form of carbon that would be strong enough to withstand the gravitational attraction from this star, and that's diamond. So they think that this planet is actually a diamond about the size of the Earth. But because it originally was a star, you have to question whether it's really a planet, because it's actually a dead star. The remnants, it's a carcass of a dead star orbiting another star, which makes it look like a planet, but it didn't start life as a planet. It just appears to be a planet now made of solid diamond. I'm sure if they could bring that back to Earth, diamonds would not be worth very much. You could buy it by the billions of tonnes. 55 Cancri, which is in Cancer. This is compared to our solar system. You can see how far Jupiter is. Its furthest planet comes out much the same distance, but it's got lots of other planets much, much further in, a lot closer. It's got about at least 5 planets orbiting it. Of course, the big ones are the easiest ones to find. So all these are orbiting stars that you probably can't find even with a telescope. Can you see any stars with the naked eye that have planets? Well, there's 25 stars that are known to have planets that are brighter than magnitude 5. So magnitude 5, you don't need a dark sight. You can see it, like if you were to leave town and head out, say halfway between here and Castlemaine, with good eyesight you would probably see it easily down to magnitude 5. Those 25 stars have at least 40 planets. So there are 25 stars that can be seen relatively easy with the naked eye, and you would be looking at 40 planets. Is there any that are easy to see? The easiest one, I had a look through a lot of lists and stuff, is the brightest star in Aries, called Hamal or Hamal. Magnitude 2, so it's very easy to see. You can see there's Aldebaran over here, that's the Pleiades. And this is taken around out this year, so it's actually sort of on the corner of a triangle, if you like, between Jupiter and Aldebaran. But it's about twice as far as from the Pleiades to Aldebaran, but sort of in the opposite direction. It's about the only really bright star, magnitude 2, in that direction. And if you look at that particular star with your naked eye, it has a planet nearly twice as big as Jupiter. So when you're looking at that star, you are looking at another planet with your naked eye. You won't see it, but there is a planet orbiting that star that you're looking at with the naked eye. Most of the others are down in magnitude like 3 or 4, but this one is actually very easy. It's one of the brightest that you can find.